of read-only memory and how read-only memory. What happened? Yeah, all of you understood the concept of read-only memory? Yes?
Yes, sir.
Okay. And also you have studied like how read-only memory can be used to implement any Boolean function. In fact, we have taken one very good example of the ASCII, hex to ASCII converter. I hope all of you understood this hex to ASCII converter. You can see it on the screen, the example which we have discussed in the previous class. Hex is represented in binary, so there are 4 inputs, and ASCII is a 7-bit code, so there are 7 outputs. This is the block diagram for the same, and this we have implemented using the ROM. I hope all of you understood this concept of ROM, how exactly it is implemented. Is it clear? You can see here once again the same diagram I have shown how it can be implemented using the ROM. There are 4 inputs and 4 to 16 decoder is used, and wherever like A0, A1, A2, A3 from the truth table, from this truth table A0 you can see here 1, 1, 0, 1, 0, 1, all these things are there. Accordingly you have to put that cross mark. Cross mark indicates there is a connection, that is 1. And if there is no cross mark, that should be treated as 0. So you just have to check the column in this particular A0. If you see, it is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, then 1, 0, 1, 0, 1, 0. So how it should be connected, you can see here. 0, 1, 0, 1, 0, 1 means wherever there is a X mark, that should be treated as 1. And where there is no X mark, where there is no connection, it is treated as 0. This is how you can implement ASCII, like hex to ASCII or binary to ASCII code converter using a ROM. And of course, since there are 4 inputs, we have to use 4 to 16 decoder. Right? That is clear? All of you understood this? Yes? Any doubts? And I have given you one homework, you can do this particular case. Now we'll move ahead. We are going to study the last part of this module 3 in your syllabus, that is programmable logic devices or PLDs. So what do you mean by programmable logic devices or PLDs? Basically, there are 2 types of programmable logic devices. Those are called as PLA and PAL. Then you may ask, what is the difference between PLA and PLA and PAL? Basically, these programmable logic devices, PLDs, are digital ICs capable of being programmed to provide different logic functions. PLDs are almost similar to the ROM structure which we have discussed just now. The general structure of the PLD is shown in the file here. You can see this is the general structure of the PLD. This is for PROM, first one that we already discussed. Now we are going to discuss about the second and third programmable logic devices called PAL and PLA. PAL stands for what? Programmable array logic, whereas PLA stands for programmable logic array. Now what is the difference between PAL structure and PLA structure? That is that you can see from these 2 diagrams here. In PLA, what happens is, okay, fine. In PLA, you can see here, basically in PLDs, there are 2 types of gate arrays used. One is called as AND array, another is called as OR array. Right? You can see in all these 3 devices, whether it is a ROM, PROM, or PAL or PLA, the structure is, in the input side, we'll be having one AND array, and output side, we'll be having the OR array. So we have to study the difference between PAL and PLA. In PAL, you can see the AND array is fusible, means programmable, whereas OR array is fixed. If AND array is programmable and OR array is fixed, it is called as PAL. Whereas in PLA, what happens? The AND is programmable and OR is also programmable, then it is called as PLA. In PAL, one is programmable, another is fixed, whereas in PLA, both are programmable. Programmable means what? You can change the connections. Like it is like in the previous case, we have seen that ROM example, we have put that cross mark, that itself is called as like a programming, you can say. Or it is changeable, we can call that, or fusible, means you can put the fuse there. So we have two different types of PLDs, PAL and PLA. So we'll discuss first one, what exactly you mean by programmable array logic. As I said, programmable array logic, right? It is a single chip solution. PALs are used similar to like they are basically used to implement sum of product or product of sum equations, like how we have done in the multiplexer logic. And the very important thing is PAL has a programmable AND array and fixed OR array. This is important characteristics of PAL that you should remember. PAL has a programmable AND array and fixed OR array. Now we'll see how exactly that PAL can be programmed, right? So normally at the input side, since it is AND array is programmable, that means at the input side you can program, but the output is fixed. The output can be used only one, and depending on your input requirement, you can program. Program means, again, you can see here, like these X marks which you have put here, they represents the programming. If the X mark is present, that means there exists a connection, and if the X mark is not present or the cross mark is not present, then there is no connection, right? So that will be more clear, right? If I take a particular example, yeah, you can take the example of this full adder itself, right? So we have to implement a full adder using programmable array logic. So programmable array logic basic structure you can see here. I hope it is visible for all, right? This is the programmable array logic structure, right? Wherein you can see I have shown three inputs, X, Y, and C in, right? So we have X, X bar, Y, Y bar, and C in bar, or X, Y, Z you can show. And then there are two outputs, sum and C out. So whenever there is a programmable, means you have to put a cross mark to indicate there exists a connection, and you can reprogram it. Fixed connection is indicated by this dot. Once you put a dot, that means that connection is fixed. It cannot be reused or reprogrammed. I hope the difference between fixed and programmable is clear. All of you understood? You have an array of AND gates, array of OR gates. Whenever you want to show the programmable connection, you have to put the cross mark. And for fixed connection, you are going to put the dot. When you put the cross mark, it can be reprogrammed. That's why it is called as programmable. You can remove that and you can put it again. That it is like a fuse structure. You can fuse it or you can anti-fuse it. Whereas fixed array means what? There is a fixed connection. You cannot remove that connection and again reuse for some other purpose. Is that clear? And if that is the case, now you can see here how it is implemented, the full adder. Like we have, you know that the full adder equations are given here. Sum is equal to X bar, Y bar, C in, or X bar, Y, C in bar, and so on. So here sum requires 4 product terms. So you can get those 4 product terms from the first 4 AND gates. Accordingly, you put the cross mark. Which you want? First you want X bar, Y bar, C in. You can see here how the X bar, Y bar, C in is put, right? That is actually, this is what is the actual connection, but in PAL, how the connection is done, that's what I'm showing here, right? So here you can see that, just take, fine. Now first term, what I want is this, X bar, Y bar, C in. So how that X bar, Y bar, C in is done? So this is X, second line is X bar. So I have put what? cross mark X bar, Y bar, and then Cin. You can see the first line I have taken here. These are the three programmable connections. Similarly, second one, X bar, Y, Cin bar. I have got here X bar, Y, Cin bar. Then this next term, fourth term, right? So all these fourth product term are obtained from these AND gates, right? So for time being, don't bother about the output thing. I will be concentrating only on the input side. Similarly, Cout I have shown by these three terms. X in, Y in, XY. So X and C in, Y and C in, and then X and Y. This is first term, second term, third term, right? So totally we have shown here 7 different or product terms we have got. Now to implement sum, what we need? This first 4. So this is the output OR array. Here we have what is called as the OR array. So OR array is fixed. So output of this, once you use, you can't reuse it. So I have shown this fixed connection. This is fixed connection. 4 product terms we have used. And these 4 are given to one OR gate. All these 4 inputs are given to the OR gate, and this will give you the sum. Right. Similarly, the next 3 product terms we have obtained here. 1, 2, 3. So these 3 are taken and given here. So this is not used. Like the last one is not used. So forget about this. We have simplified expression we have used. If you don't use the simplified, then we would have got here also 4 terms. So these 3 are connected to this, and we got the final carry out. So this is how we can implement a full adder using what? Programmable array logic. I hope all of you understood it. It is like a normal logic diagram what you will be drawing, but one side, input side, we have a programmable array, and the output side we have fixed array. So programmable means you can reuse that, but since output is not programmable, it is fixed. You can use it only once. Like suppose if the same product term, assume that this is the same product term you are having, this may be required in the Cout also. So I can't use it here. I can't put the dot here also, because already this is used here, so you can't use it. So if you require once again, then you have to create one more here, and that can be used for Cout if you are using what is called as programmable array logic. If it is a programmable logic array, there both are programmable. So you can put cross marks and you could have reuse that. But in PAL, you cannot reuse it. Is that clear? This is the structure of programmable array logic. This is for what? A PAL with 4 inputs and 4 output is shown. One example is shown, which is having, see, all programmable AND array, all the connections are made, and depending on which term you want, you can take. Say these 4 are used to get the function y3, next 4 are used for y2, then these 4 are used for y0, and these 4 are used for y0, right? So for every product term, you can use a single OR gate, and whichever you want the product term, just put the dot, and that can be used to the OR array, and that OR array is fixed. So that is programmable array logic. Now this is a general structure wherein I have shown what all the fuses are present. Now depending on your requirement, what product term you want. Now here what is happening is you have given A as well as A bar, B B bar, C C bar, D D bar. So obviously what happens is this becomes 0. Yes or no? Because you have given A as well as A bar, A and A bar, B and B bar, C and C bar, D and D bar. So all we will be getting output as what? 0 only. All will be 0, so that all these outputs y0, y1, y2, y3 will be 0. That's why we should not put fuses for all. Depending on what product term you want, you have to retain only those fuses or those connections, and other connections you have to remove. It is like ready-made. You have all the connections, whichever you want you have to retain, and others you have to remove. That is what is called as programming of the AND array. Now in this, what we have done is, you can see here, whatever I want the expressions for y3 as what? A bar, B, C bar, D, or some example I have taken. accordingly. You can see here the first Y3, if you want to see, in that the first term is A bar B, C bar D. That I have obtained here. A bar, B, C bar and D. So this I have to use for Y0. So I have to put here what? The dot. Similarly, second term you get from the second and get third, fourth, and these four should be used for Y3. Similarly, next I need what is this 3 Y2. For Y2 I need 1, 2, 3. So use this 1, 2, 3. This, though it is connected, but there is no connection here. Or you can remove this. Right? Only these 3 are used. Even if you show this 4, but there are no input program, so this will not be having any effect on this. Similarly, here I need 4. Those 4 can be obtained here. And lastly, I have only one A, B, C, D. So I have shown all because they are fixed. You can't remove them. But this is programmable this side. Input side it is programmable. So you remove all the fuses. Since this is fixed, it is not possible to remove this. So we have retained these 3. But you have not connected any inputs here because this side you have a flexibility to program it. So obviously I have programmed only one gate and we'll be getting this, and that is connected as the output. So this type of programmable logic device is called as programmable array logic. Hope it is clear. Yes? All of you understood that or no? See, there is no response from anybody. Are you getting it or no?
Yes, sir.
Right. Next, programmable logic array. This is very important, wherein, as I said, both are programmable. AND array is programmable, whereas as well as OR array is programmable. Now, can anybody tell me what will be the difference between PAL and PLA then? In the structure, the same logic diagram which we have shown here. If you want to implement this using PLA, what changes you need to do? Yes? Suppose if the same circuit you want to implement using PLA now, not PAL. Like, you should not get confused between the words PAL and PLA. In PAL, only A and array is programmable, whereas PLA, both are programmable. That is how you have to remember. So what changes you need to do in this? If it is a PLA, both are programmable, so you need not put a dot. Dot means it is fixed, right? You can't reuse that. So if you put a cross according to your requirement, output side is also programmable. So that device is called as programmable array logic. So one example I have shown here, wherein I have shown the fuses. So the same fuses you can show by a star mark, and you can implement these functions. So here I have given PLA with 3 inputs, 5 product terms and 4 outputs. This need to be implemented, right? F naught equal to sigma m 0146, whose equation is given by A bar B bar plus AC bar, then F1, F2, F3. How it can be implemented, you can see there, right? So you want A bar B and AC bar. You should get that A bar B bar. I have got it as A bar B bar here. This term needed is A bar B bar and AC. So you can see A bar is connected to this line as well as B bar is connected. So A bar and B bar together will be available here. Similarly, next what is connected here is A and this is C bar. So on this line, your second product term AC bar is available. Next, you can see here only B is connected. You can see that. Next here B and B C bar is available, right? And lastly, this is B C bar, and lastly what we get is A and C, right? So to implement F0, what we need now? To implement F0, we need 2 terms. Which 2? First and second. So here you can see connection is shown, first and second, right? It is equivalent to, like, you can just put a cross mark. That's what the normal, this is, I have shown the fuse level diagram, right? Actually it is like having one star mark or X mark here, then one X mark here, then putting X mark here and putting X mark here to implement F0. Right. Similarly, for F1, F2, and F3, this is how we can implement this. The same functions which are shown can be implemented like this now. A, B bar. This is the diagram we have shown. Actual gate level diagram we have drawn, but normally what we do is we will not show these inputs A bar and B bar separately. Just we can show one line and you can put cross mark for A bar and B bar. This is equivalent to showing these two lines. Is this clear? Similarly, here A and C bar is required. Instead of showing two, you put one cross mark here and another cross mark here. Then B. The next for this, you can show it like this. That is B and C bar. And for here also, you can show it as A. Here one you should show, and sorry, for this line, and then you should show it as C. Similarly, here two are required. You can show like this. One line itself, this and this. Only one line you can show for this OR gate instead of showing two. Then similarly, you can show only one line here. Take this and this. Similarly, for this also, you can show only one line and you should mark these two. And here you can show one line and you can mark these two for that. And that is the construction of programmable logic array, right? So we have implemented programmable the given equations, the four output functions and three input variable functions using the programmable array logic, right? Now sometimes we have to implement this by using what are called as reduced PLA table. Right, this is very important from your examination point of view. All of you just have attention here. Before that, all of you understood the difference between PAL and PLA? Yes? Have you understood the difference between PAL and PLA? It is similar to what you have studied like a ROM only. But only thing, as I said, in PAL, only AND array is programmable or array is fixed. Whereas in PLA, both are programmable. Is that clear? This general diagram you should remember. AND array, OR array. AND array is programmable, OR array is programmable, then it is PLA. And if only one AND array is programmable, OR is fixed, then it is called as PAL. Any doubts here? All of you understanding or no?
Yes, sir.
Any doubts till this point? Like afterwards, you should not say that I have not understood this, not understood that, because next important part I am going to cover, and it is almost the last part of this particular module actually. That is reduced PLA table, or what is PLA table, and how we can implement any Boolean equation using reduced PLA structure. Any doubts? If there are no doubts, I will proceed further and I will take the last part of this module that is called as PLA table, how to construct a PLA table. Yes, can anybody explain me what exactly you mean by PAL and PLA and the major difference between PAL and PLA? Anyone? Yes, Adnan, are you there? Aditi? Yes? See, there are no response, only, I don't know. That means you have not understood this concept at all. Jyoti, can you explain the difference between PLA and PAL? Yes? See, I'm not getting any response from anyone. Yes, Omkar? Aniket?
In AND
Yes,
array,
sir.
sorry.
Yes?
So in PAL, only the AND array is programmable and OR array is fixed. And in PLA, both are programmable.
Okay. So how you represent a programmable array and a fixed array?
So a programmable array can be represented by X mark and a fixed array is represented by a dot.
Dot. Okay. So if a particular, say, a product term is available, can you reuse it in a fixed OR array? A particular product term you need more than once or more than one functions, output functions. Say there are different output functions, F0, F1, F2, F3. You need the first product term generated by the first AND gate, say in F0 as well as in F3, right? So how you can use this in PAL structure and in PLA structure? Are you getting my question, Aniket?
So so you're asking like output.
Yes, I have one single product term, and that single product term I need in two different output functions. So how I can use this in PAL? This is the simple question I have asked you. Yes?
Sir, in PAL, we have to take another product, but in
Yes.
PLA, in the same product we can merge, sir.
Yes. When you want a same product term more than once in PAL, you have to generate that product term again and again, number of times, how many times that particular function product term is required in the different output functions. You can't use the same, right? So first product term you have used F0, you can't use it again in F1. So what you should do then? You have to generate that product term again by using different AND plane, and then you can use it. Whereas the same thing if you want to implement it PLA, how you can do it? I need one product term in more than one output functions in PLA. How I can do that? Whether I need to generate that product term twice or a single product term which is generated by one AND gate, I can use it in the multiple output functions. Yes, Omkar?
Sir, I am not getting question.
You are not getting the question.
No,
I
sir.
am asking, I want to implement some function, right? In that, I need one product term, right? For example, say A bar BC. Assume that there are three input and A bar C, A bar BC. This is the product term I need in output function F0 as well as in F1. Two different functions it is required. How I can do or use this in PAL structure and in PLA structure? That is my simple question to you. Got the question now, Omkar?
Yes, sir.
Can you tell me the answer? Or anybody else? In fact, I have given you the answer just now. If it is PAL, if you want that particular product term more than once, then what you need? You have to use those many AND gate outputs and give it to that respective output OR gate. You can't use the same because you are putting dot there, that is fixed. Whereas in PLA, what you can do is, you can use it. You can put two cross marks on the same output line, that same product term, and you can use it in F0 as well as in F1. I hope it is clear now.
Yes,
You
sir.
need not generate that product twice. Whereas in PAL, how many times you want to use that product term, those many times you have to generate using what is called as the AND gate. Fine? Okay. So now we'll see how to prepare what is called as PLA table. Now to prepare the PLA table, what we need to do is, first we need to find all the distinct product terms which are required to implement multiple output functions. Now, can anybody tell me here how many output functions we are having? This is very important part now to generate the PLA table, right? How many outputs we are having here?
4, sir.
4.
How many outputs? How many output functions we are having?
4.
4.
4.
What are those? F0, F1, F2, F3. Right. And how many input variables we are having?
3, sir.
3. What are those?
ABC.
What are those? The 3
A, B,
input variables are indicated by what? Or denoted by what? Yes?
ABC.
A, B, C. Then these 4 functions F0, F1, F2, F3 are simplified. Separately it is simplified. We got the product term. What are the 2 product terms that are required for F0? Yes?
A bar, B bar plus
A bar, B bar and
AC bar.
AC bar. Similarly for F1, B and AC bar. For F2, A bar, B bar and BC bar. And for F3, there are 2, that is AC and B. So totally 4 functions are there. Each function uses 2. Totally 8 product terms are there. But all 8 are not distinct. Like same A bar, B bar is repeated in 2. B is repeated in 2. A, C bar is repeated in 2. So how many distinct product terms we need to implement these 4 functions? Yes. You have to write one by one. First write A bar, B bar. Then write A, C bar. Then write B. Next A, C bar already you have written. Don't write again. Then A bar, B bar is already written. Then write B, C bar. Then A, C. B is already written. So if you see here, totally how many different distinct product terms we are having in this particular expressions, the 4 expressions what we are having. We are having how many?
5.
6. 1, 2, 3, 4, 5. Sorry, 5. Because 3 are repeated. So 3, those minus, so 8 minus 3 is 5. 5 different product terms we are having. So first column in the PLA table is the distinct product terms you write. So write A bar, B bar, then A, C bar, B, B, C bar, A, C. Now these product terms you have to represent in terms of the input variables. What are the 3 inputs we are having? A, B, C. Right. So A bar, B bar means what? How do we represent A bar, B bar? In terms of zeros and 1 by considering the inputs A, B, C. A bar, B bar can be represented as what? A bar means 0, B bar means 0, but here C is not present in this product term. Since C is not present in this product term, you need to write that as what? Dash. Is this clear? Similarly, how do you write A, C bar? A means A is 1, B is not there, C bar is there, means 0. Only B is there means B is 1, A and C are dash. B, C bar means what? A dash, B1, C bar means 0. Then A and C 1, 1, B is dash. This is very important thing that is you have to write in terms of the PLA table. And then there are how many outputs? 4 outputs. F0, F1, F2, F3 you write. Now this is very important. Can anybody explain me how this particular outputs are written here? Yes? All of you getting it, no? First column is the distinct product terms. Then write those product terms in terms of 0, 1s and dash by representing the inputs, whatever are there. Then you have to write the 4 outputs, F0, F1, F2, F3. Can anybody tell me how these outputs are written here? Because in the outputs column, I have written some places 1 and some places 0. Right? You can see here 1 is there, here 0 is there, again here 0 is there, here 1 is there. How that 1 or 0 is written there? Can anybody tell me? To write this output, you need to go back to these main equations. What you need to check is, when you are writing outputs F0, F1, F2 for the product term A bar, B bar, you need to check whether A bar, B bar is present in which of these four outputs, and if A bar, B bar term is present any of these outputs, there you write 1 and others you write 0. So in which functions A bar, B bar is present? Which functions A bar, B bar is present? You can see here. A bar, B bar is present in F naught and it is present in what? F2. So what I should write? F naught equal to 1, F2 equal to 1, and the remaining 2 should be 0. Like that. A C bar is present where? A C bar is present in F naught, F1. So write F naught and F1 as 1, 1, others 0. B is present in F1 and F3. You can see here F1, F3. Similarly, B C bar, AC. AC is present only in F3. So you write F3, others are 0. So this table, what we have drawn is called as reduced PLA table. You need not write all the input combinations. Only based on the product terms, which are distinct product terms required, we have written this, and this is what is called as the PLA table that is used to implement any Boolean equation using PLA. All of you understood what is PLA table? How PLA table is constructed? Any doubts? Any doubts here? Right. Then that's what the PLA realization of these equations. One more example is given now. You can try this as a homework. If you understood this easily, you can do the PLA realization and you can see the different equations what you have got. A bar BD, you get that A bar BD by putting cross marks here, right? And if the same you are using, whatever the terms are there, you can just put the cross mark in the output also, because this is OR array and this is AND array. Both are programmable here, right? Since both are programmable in input side as well as output side, you have to put the cross marks and get these product terms, right? And accordingly, you can get this PLA table. Already I told you how to write the PLA table based on how many different functions you are having. 1, 2, 3, 4, 5, 6 I have written, but actually here product terms are 1, 2, 3, 4, 5, 6, 7, 8, 9. Though there are 9 product terms, 6 are different, distinct. Those 6 are written here and those 6 will be used in PLA implementation also. You need not implement all. So you can see wherever the double thing is there, you will get 2 cross marks on the output line, and that can be connected to the output functions like here in case F1, F2 and F3. Right? That is the implementation of this. And this is programmable array logic. You can just try example using PLA of that 7-segment display, which we have discussed already, right? I want all of you try implementing 7-segment display using PLA. This is a homework. This is also very important example. Everybody should try implementing 7-segment display or 7-segment decoder or decimal to 7-segment decoder using PLA. So how you should implement that? 4-bit decimal input you can show by A, B, C, D, and you can show these 7 outputs A, B, C, D, E, F, G, H for this FND or 7-segment display. Generate the truth table, and from the truth table, this in fact it is given here, from the truth table, right, directly you can give the PLA implementation. This is called as PLA implementation. In PLA implementation, again I am repeating, this is called as AND array and this is called as OR array, and you can see here both are programmable. So this is also a very important example from your examination point of view. 7-segment BCD to 7-segment decoder using PLA, right? Already we have implemented this using decoder. It can be implemented using PLA also, right? That's what you can do it. PLA's examples, the other examples are given here. You can see one more example is given. F1 equal to sigma 0146, F2 equal to this, F3, F4, 4 functions are given. Draw a PLA circuit, simultaneously realize. Hello, sir. Hello. Hello.